All right, in this video, we are going to connect Green's theorem to the two-dimensional curl and divergence of the vector field F. Okay, so for what we'll call the circulation form of Green's theorem, okay, I'm going to write this integral on the left that you see in Green's theorem in the form we wrote it in section 15.2 it was. So that we wrote the circulation along this curve C for the vector field as the integral of f dot t, where t is the unit tangent vector to your path as you move along, and this integral is taken with respect to arc length, so we have a little ds there. Okay, so these two things mean the same thing, and in that section we argued why both notations are appropriate for what we're measuring. The nice thing about this notation is just really emphasizing that as you move along this boundary, you are looking at the tangential components of your vector field f, and this integral is just summing all those various tangential components, giving you the what we call the circulation of the field along that boundary, right? It's how much this path C will actually see the vector field f, okay? So the thing on the right here, well, we recognize that integrand as just what we define to be the two-dimensional curl of f. So we can write that as just the curl of f. And now what I'd like to do is argue why this statement is true. Okay, so just for simplicity, let's take the curve C just to be a square. And so this is oriented counterclockwise here. And so this integral off to the left, as I just said, right, this is measuring our tangential components. So these little vectors I drew in blue, these are the unit tangent vectors t as we move along the boundary. And this integral is just measuring, right, the scalar projections of your vector field f onto these blue vectors, and then it's just going to sum those projections up. Okay, now I'm not going to draw the vectors for f in this picture just because it makes things too cluttered. Okay, but what I want to now look at is what the right-hand side is doing. Okay, so we said that the curl of f is measuring the rotation of the vector field at a point. Okay, so if I think about each one of these little sub-squares as being really, really small, okay, and I want to know, okay, how is my vector field rotating objects, say, nearby this point? Well, a way I can measure that is just to measure the circulation of the vector field along the boundary of this little sub-square right here. Okay, now as far as the orientation of this little square, well, I want the region inside of this square to always be off to my left as I move along the boundary. So I'm going to have to move like this, and then I'm going to have to go up like this. So as I move along this little square, this interior region is always off to my left. Okay, what about this square? How would I orient that? Well, I'm going to have to go down, then over, then I'm going to have to go up, and then when I come over here, oh, notice I'm actually going to be moving in the opposite direction as this. So when I look at the circulation of my vector field on, say, this boundary and then on this boundary, the two contributions along this common edge are actually going to cancel out. Aha, okay. Let's move over to this square. How do I have to orient this thing? Well, to have this interior region always off to my left, I'm going to have to move like this. And then when I come down here, okay, I think I see what's going on now. See, the contributions here are going to cancel out because they have opposite orientation. Likewise, for this square, I'm going to get cancellation here as well as here. So these are going to cancel out. So what I'm saying here is that by looking at the circulation of our field along each one of these little subsquares, what we're really seeing is that we're just going to see the contributions on the boundary as the things that are actually going to in net actually contribute. All this stuff inside is going to wind up canceling out. Okay, so we can say that as follows. The net rotation of F throughout your region D, which is really what this integral on the right is measuring, it's equal to the circulation of your field just on the boundary. And that's exactly what this integral on the left measures. Okay, so that's really the essence of what Green's theorem is saying, at least when stated in this circulation form, right? Is the internal rotation. Okay, when you sum it all up, you get all this internal cancellation, and so it all just comes down to what is going on the boundary. All right, cool. So now let's move on to what we're going to call the flux form of Green's theorem. Okay, so first thing I want to remind you of is that in section 15.2, okay, we introduced the flux integral, which is just this line integral of our vector field dotted with the outward unit normal vector n, and this was taken again with respect to arc length. Okay, so we had also written this integral right here in terms of the components of the vector field f, right? This was p dy minus q dx. Okay, so what I want to do now is first, let's go ahead back to the circulation form, remind ourselves what the circulation integral looks like in terms of the component functions. And the reason why is that it's going to then help us determine what the appropriate integrand should be for the double integral over here when we're thinking about this flux integral off to the left. Okay, so for the circulation form, okay, we had written this circulation integral as the integral of p dx plus q dy. Okay, so according to Green's theorem, the thing that's multiplying the differential dy, this gets differentiated with respect to x over here. Now, the thing multiplying the differential dx, which is p in this case, it gets differentiated with respect to y, and there's a negative stuck in front of it. Okay, so coming down here, the thing multiplying the differential dy, which is now p in this case, okay, it's going to get differentiated with respect to x. So I'm going to have partial p, partial x. And now the thing multiplying the differential dx is negative q as opposed to p. And what we set up here is that it's going to get differentiated with respect to y. So we're going to differentiate negative q with respect to y, but then we're going to stick a negative in front. So all in all, we're going to get plus partial q partial y. Okay, so these two statements really are the same thing, except we're just relabeling the component functions. Okay, so what does this integrand right here remind you of? Well, that of course is just the divergence, right? We define the two-dimensional divergence to be this quantity partial p partial x plus partial q plus partial y. So what we're saying here is that Green's theorem says that this flux integral is equal to the double integral over this region D of the divergence of our vector field. Okay, so like we did up above, let's think about why this is true. Okay, so the flux integral is measuring the outward flux of our vector field along the boundary here. Okay, so along this path C. And what this notation is saying is that you're taking now the normal components of your vector field as you move along this path C, and then you're going to be summing those up. So these little green vectors are the vector n as you move along this square. Okay, much like the blue vectors up here were the unit tangent vectors, these are the unit normal vectors. Okay. So this thing is just, again, measuring that normal contribution of your vector field as you move along the boundary. So what's the thing on the right doing? Well, that's where we're going to look at what's going on inside the region. And we said that the divergence is measuring the flux density of the vector field at a point. Okay, so put another way, if I imagine, say, I'm at a point in this square in the upper left-hand corner, okay, I want to know, okay, what my vector field is contributing in terms of, say, outward or inward flux in this little region near my point. Okay, so like we did up here, let's first think about how we're going to have to orient things for the boundary of each one of these little subsquares. Okay, so it's really the exact same orientation that we saw up there. So we're going to have to move like this for this square. And then for this square down here, we're going to have to move like this. And then we're going to get opposite orientation there. And then likewise up here, we're going to move like this for this square. And then we're going to have to come down here. These have opposite orientation. And then we're going to get for this last one up here and here. And so now what we're doing, okay, so for each one of these little subsquares, okay, so if I'm thinking about this one right here, okay, I'm really thinking about measuring the normal component of my vector field along this edge as I move from left to right if I'm thinking about this square. But see, if I'm thinking about this square and I want to measure, say, the net flux across its boundary, see now, since I'm moving from right to left, that normal would point actually outward like that. So it's going to point in the opposite direction. And again, we're going to get cancellation here. And likewise for all of these others. Okay, we're going to get this cancellation on the inside of the region. Okay, and so if I want to know what the net flux is of my vector field throughout the entire region, well, it's all going to just come down to what's going on the boundary. Okay, so I say here the net flux of your field throughout D is equal to the flux of the field F across the boundary. Okay, so this integral on the right, it's measuring the net flux throughout the entire region. And since you get all this internal cancellation, okay, the net flux then is just determined by the flux of your field across the boundary. And that's exactly what this integral on the left measures. All right, cool. So with all of that in mind, we'll go ahead and tackle the last few questions on the worksheet, and I will see you there.